Assalamualaikum and hi doctor. My name is Nur Dina AKRAM and my number matrix is 227695. So today, me and my group will present about the thermodynamic analysis of the oleochemical industry, and my group consists of Fatin, MAISARAH, INTAN, NABILA and me. So our presentation will begin with a brief overview of the industry and its importance, followed by an overview of the global oleochemical market. Next, we move on into we will discuss the production process and the main type of the oleochemical product, which is it have three. Firstly is the process one, which is fat splitting. Next is the transesterification, and lastly is the fractional distillation. Next, we look into the comparative guide, which is thermodynamic in oleochemical processing. After that, we will conclude the presentation and also there's some reflection into our discussion. Firstly, let's look at what the oleochemical industry is. So, oleochemicals are chemical products derived from the natural oils and fats, mainly vegetable oils such as palm oil, coconut oil, soybean oil, and animal fats. Unlike the petrochemicals, which are produced from crude oil, oleochemicals come from renewable and biodegradable resources and making them more environmental friendly. The industry mainly produces fatty acid, fatty alcohol, glycerin, and fatty ester. These products serve as the essential raw materials for manufacturing soap, detergent, cosmetics, personal care products, lubricants, pharmaceuticals, food additives, and even bio-based plastics. Next, I will discuss about the importance of the oleochemical industry and its global application. The oleochemical industry is increasingly recognized as an important sector because it supports the transition toward more sustainable and environmentally responsible manufacturing. One of its key advantages is that oleochemicals are derived from renewable resources such as plant oil and animal fats. Unlike the fossil-based feedstock, these resources can be continuously replenished, making them a more sustainable option for a long-term industrial use. In addition, oleochemicals are biodegradable, meaning they can naturally decompose in the environment. This characteristic reduces their environmental impact and makes them a preferred alternative to many petroleum-based chemicals, particularly as the industry seeks to comply with a stricter environmental regulation. Another significant advantage is their versatility. Oleochemicals serve as essential raw materials in a wide range of industries, including the personal care and also the biofuels. Their diverse applications demonstrate their importance in supporting both industrial production and everyday consumer products. Asia also plays a significant role in the global oleochemical industry. As one of the world's leading producers of palm oil, the country provides a reliable and abundant supply of feedstock for oleochemical manufacturing. As indicated on this slide, Malaysia produced approximately 19.9 million tons of crude palm oil, highlighting its contribution to the global supply chain. In terms of global application, oleochemicals are widely used in the production of cosmetic and personal care products, where they function as surfactants, emollients, and emulsifiers. They are also incorporated into food additives utilized in the production of biodiesel, particularly fatty acid, methyl ester of FAME, and applied in the formulation of lubricants for industrial and automotive use.
Now, I will continue to explain the overall process flow of oleochemical production. We start with the feedstock oils or fats such as palm oil, vegetable oil, or tallow. These undergo fat splitting, also known as hydrolysis, where triglycerides are broken down using high temperature and pressure water. This produces crude fatty acid and also glycerol. Next, the fatty acids are purified through fractional distillation under vacuum conditions, separating them into components like lauric acid and also oleic acid. Finally, through transesterification with methanol and also a catalyst such as NaOH and KOH, we will obtain fatty acid methyl esters, FAME, commonly known as biodiesel, along with glycerol and also glycerol as a byproduct. This diagram gives us the big picture of how natural oils are converted into valuable oleochemicals. Let's zoom into the first process, which is fat splitting. Triglycerides are broken down into fatty acids and also glycerols using high temperature and high pressure water. The chemical reaction is one triglycerides molecule reacts with 3 water molecules to form glycerol and 3 fatty acids. In industry, the Colgate-Emery process is widely used. It is a continuous countercurrent flow system that requires no catalyst and achieve conversion rates of up to 98 to 99%. This makes fat splitting highly efficient and practical for large-scale oleochemical production. Next, let's talk about the thermodynamic analysis of process 1, which is fat splitting. So the first one is thermal effect. It is between 150 degrees Celsius and 280 degrees Celsius. The reaction shows no significant heat change and it is thermally neutral with delta H approximately equals to 0. The next one is energy requirement. Even though the reaction itself doesn't require heat, energy input is needed to reach operating temperatures of 250 to 330 degrees Celsius to maintain water in liquid phase under high pressure and provide steam for stripping. Typically, about 26 pounds of steam are required for 100 pounds of tallow. Lastly is about Gibbs free energy. The key driving force is entropy. The Gibbs free energy equation is delta G equals to delta H minus T delta S. So at high temperature, the minus T delta S term becomes more negative, making the reaction thermodynamically favorable.
Good day everyone, so I will continue with process 2, which is fractional distillation. After hydrolysis, a crude fatty acid mixture containing different fatty acid is produced. So the purpose of fractional distillation is to separate this fatty acid into high purity individual components based on their boiling point difference. This separation is important because different fatty acids have different industrial applications. For example, lauric acid C12 is used in soap and cosmetic. Palmitic acid C16 is used in food and pharmaceuticals, while oleic and stearic acid C18 are commonly used in lubricants and cosmetic. This slide highlights the thermodynamic principles behind the separation process. Fractional distillation is one of the most energy-intensive stages because heat must be supplied continuously to achieve vaporizations. The separation depends on differences in vapor pressure and relative volatility between fatty acids. Components with high volatility vaporize more easily and can be separated more efficiently. Operating under vacuum improves separation efficiency while reducing energy consumption and maintaining product quality. After purification, the fatty acids undergo transesterifications. In this process, fatty acids react with methanol in the presence of catalysts such as NaOH or KOH to produce fatty acid methyl ester, or FAME, which is biodiesel. This step is important because it converts fatty acid into a valuable renewable fuel with improved combustion properties and lower viscosity. The reaction is typically carried out at 55 to 65 degrees Celsius at atmospheric pressure and a methanol to fatty acid ratio of approximately 6 to 1. From a thermodynamic point of view, transesterification is mildly exothermic reaction, meaning it releases a small amount of heat. A catalyst is used to lower the activation energy and increase the reaction rate. Another important principle is Le Chatelier's principle. Excess methanol is added to shift the equilibrium toward biodiesel productions, resulting in a higher conversion rate. In conclusion, thermodynamics plays a key role in both fractional distillations and transesterification by optimizing temperature, pressure, and reaction conditions to maximize efficiency, product quality, and biodiesel yield. That's all from me. Thank you.
Now, let's dive into comprehensive comparative guide of the three central pillars of industrial oleochemical processing. Understanding how thermodynamic principles govern each individual route is essential for both design and operational optimization. So first, let's explore fat splitting, or called hydrolysis, on the far left. So this process is driven primarily by liquid-liquid phase equilibrium because this is a highly endothermic process. It requires elevated temperature of 250 to 330 degrees Celsius and sustainable pressure of 4.9 to 8 megapascal. The excess water acts as both a reactant and the driving force to push conversion to an impressive 98 to 99% limit. Next, we're moving to the center column. We see transesterification or alcoholysis, which is fundamental to modern biodiesel production. Unlike hydrolysis, this reaction operates under much milder conditions between 60 to 80 degrees Celsius and at simple atmospheric pressure. Here, thermodynamic is all about chemical equilibrium constraint. To drive the fraction forward, we use excess methanol and select catalysts to achieve the desired yield. And finally, on the right, we have fractional distillation. This is purely physical separation process governed by vapor-liquid equilibrium, VLE. We employ a high vacuum of 1 to 10 kilopascal to lower boiling point, allowing us to safely separate valuable fatty acid by their unique boiling point difference at temperature between 110 to 200 degrees Celsius without thermal degradation, reaching over 99% of purity. Moving on, let us reflect on the role of thermodynamic in industry. The thermodynamic is not just a collection of abstract calculation. It serves as a highly practical central engineering tools. In core application, thermodynamic drive process design. By evaluating enthalpy, Gibbs, free energy, and equilibrium constant, we determine whether a reaction can physically take place and define its maximum theoretical yield. We also use this principle to establish operational trade-off. For example, balancing temperature and pressure to prevent product degradation in our distillation column. Importantly, phase equilibria data, specifically liquid-liquid and vapor-liquid data, is absolutely vital. Without precise VLE data, sizing separation column and choosing the correct number of stages is impossible. And finally, we must always balance operational trade-off. Higher temperature accelerate reaction kinetic but threaten product degradation. Higher operation pressure can favor equilibrium conversion but will also exponentially increase our capital and equipment costs. To conclude our presentation, let us summarize our key conclusion on thermodynamics in the oleochemical industry. The fundamental role of this industry is converting renewable fat and oil into highly diverse, valuable products. Every stage of this transition is governed strictly by thermodynamic rules, whether it is the phase equilibria of fat splitting, shifting the chemical equilibrium of transesterification using excess reactant, or using vacuum VLE for fractional distillation. Operational optimization will always require a delicate balance. We must consistently with reaction kinetic against equilibrium limit, minimize overall energy consumption while maintaining product quality and secure high conversion without triggering thermal degradation. Understanding and mastering thermodynamics is the ultimate foundation for efficient, green, and modern process design. So, here is the list of academic and industrial reference that support the science behind this work. This document ranges from holistic, foundational industrial process like the 1948 College Emerald fat splitting pattern to modern study examining thermodynamic properties of triglyceride and methanol synthesis. Our distillation and fractional process are grounded in rigorous scientific modeling, relying on established equation of state and modern exergy analysis technique to ensure maximum efficiency. With that, I would like to say very big thank you for your time, attention and engagement today. Thank you.